I'm Martino Bernasconi and I'll be presenting No Regret Learning in Bilateral Trade via Global Budget Balance, which is a joint work with Matteo Castiglioni, Andrea Celli and Federico Fusco. Bilateral trade is a setting in which we wish to design mechanisms that help a buyer and a seller trade some good. We would like this mechanism to have some properties such as that maximize the social welfare, that is both incentive compatible and individually rational, and in some sort of ways budget balanced, which means that the mechanism should not give subsidies to the agents. However, the Myerson-Setter-Wire theorem says that such a mechanism cannot exist. Literature thus focuses on simple mechanisms such as fixed price mechanisms, or in the Bayesian setting in which we have access to the distribution evaluation of the buyer and the seller. More recently, the problem was casted into an online learning setting in which the knowledge of the distribution of buyer and the seller evaluations are relaxed, and it has to be learned by a learning agent by a repeated interaction with the buyer and the seller. In this setting, at each time t, arrives a new pair of seller and buyer, and each comes with its own private valuation, which is ST for the seller and BT for the buyer. The learning agent then posts two prices, PT to the seller and QT to the buyer. At this point, a trade happens only if both the seller and the buyer accept the trade, and this generates a gain from trade, which is the sum of the utility of the buyer, the utility of the platform, and the utility of the seller, but everything cancels out, and we are only left as the difference between the valuation of the buyer and the valuation of the seller. The goal is to have a low regret, which is the difference between the best pair of fixed price and insight and the value and the utility gained by the learning agent over the interaction. Ideally, we would like this quantity to grow sublinear in T, which means that asymptotically the per round performance is equivalent to the one of the best fixed price. Also can be proved that the best pair of fixed price and insight it's equal for the buyer and the seller, and we can focus on a single price. Now we are going to focus on budget balance. The strongest notion of budget balance is the one of strong budget balance, in which the platform proposes the same price to the buyer and the seller. However, it can be shown that there are instances in which this assumption is too strong and we cannot learn anything in this setting, and the regret grows linearly with the time horizon. And the lower bound is shown by showing two instances in which they are completely equal from the point of view of the learning agent, which means that they have exactly the same feedback, but they have two very different optimal prices. The key point here is that the lack of observability of the social welfare of a trade is what makes the learning objective difficult in this setting. The crucial problem is that if we post the same price to the seller and the buyer, for example 1/2, there can be two cases in which the valuation of the seller is 0 and the valuation of the buyer is 1. In this case, the trade will happen and the gain from trade will be 1. However, there can be the case in which the valuation of the seller and the valuation of the buyer are equal to 1/2, which is the price we are posting to them. So the trade will be accepted, but the gain from trade in this case will be 0. However, the learning agent cannot distinguish between these two cases. We can get around this situation by defining a weak budget balance, which simply means that each time step the platform does not give subsidies to the markets, but we can post different prices to the buyer and the seller. Indeed, in the case of weak budget balance, it was proved that there exists an estimator which, given a price P, toss a biased coin with probability P. If the result of the coin toss was head, then we are going to draw a uniform price and present it to the seller, while present to the buyer price P. And in the other case around, if the result of the toss was cross, then we are going to draw a uniform price and present it to the buyer, and this price is drawn from P1 and present the price P to the buyer. This simple estimator was proved by Azar et al. To be an unbiased estimator for the gain from trade at a specific price P. Thus, by relaxing the STOC budget balance assumption into the weaker one of weak budget balance, we can prove some positive results. For example, in the case of a smoothed adversary, in which the adversary can pick distributions that are not too concentrated, then we have t to the 3/4 regret. And without the smoothness assumption, we can have a 2 regret guarantee of t to the 3/4 and a lower bound that shows that an algorithm can do better than regret of t to the 2/3. Another fundamental problem, other than the lack of observability, is that the action space is too large. And a needle in the haystack problem can arise in such a setting. For example, if we have 0 valuation for the seller and p valuation for the buyer, or p valuation for the seller and 1 valuation for the buyer, then posting p wins both trades, but only posting p and finding that p is the right price to sell is unfeasible. We solved both of this problem by introducing the global budget balance assumption, which means that the revenue, which is actually the utility gain from the platform, updates a budget, which initially is 0, and the only requirement that we have is that over the total interaction, the budget is greater than 0, which means that the platform does not subsidize the market. In the global budget balance setting, then without any assumption on the behavior of the buyer and the seller, we can prove that there exists an algorithm which guarantees a regret of t to the 3/4, and we complement this result by almost matching lower bound, which states that no algorithm can achieve more than t to the 5/7. The general idea of our algorithm is to divide the time horizon in 2 phases, and in the first phase, the algorithm will run a revenue maximization step, and in this phase it will collect some budget, then it will be reinvested in the second phase by allowing to post non-budget balance prices, and this will allow us to overcome the negative results. So the crucial step is to show that in the first phase, in the budget collection step, we are not collecting too large regret. The first phase is done by running bandit algorithm on a multiplicative additive grid that has 2 key properties. That the cardinality of such grid is small, and the revenue of the best prices for the revenue is close to the maximum that we can have in terms of gain from trade. This is the crucial property of our algorithm that says that the maximum gain from trade is not larger than a multiplicative logarithmic factor over the best price in terms of revenue. Thus, we can run our favorite bandit algorithm in the multiplicative additive grid until we collected enough budget. What this proposition shows is that the regret with respect to gain from trade does not suffer too much in this first phase. The key property of our algorithm in the second phase is that it posts slightly non-budget balanced prices on a grid in which the prices posted to the seller is 1 over k larger than the price posted to the buyer. And this not only gets around the problem of the needle in the haystack, but it gets that our revenue is decreased only by a factor of 1 over k. And thus we can design a non-regret algorithm with respect to the best fixed price in HK, which dominates every price in which the price posted to the buyer and the seller is equal. And this, together with the estimation and the block decomposition that converts any full feedback algorithm into a bandit one, we are able to prove that in the second phase our algorithm suffers small regret. The general idea of our proof is to fix our budget to be T over K, so that in the second phase we have enough budget to not care about revenue. Then we decompose our regret into two main parts, A and B. A is the regret, is the gain from trade suffered by the algorithm in the first phase, and B is the gain from trade collected in the second phase. The first part, it's taken care by proposition star, which converts it to a regret of at most the amount of budget, and the second term is given by the regret of our bandit algorithm. Thus, setting the budget to be t to the 3 over 4 and k, the number of arms, to be t to the 1 over 4th, we get our regret upper bound of t to the 3 over 4. Our lower bound is inspired by past lower bounds in the smoothed adversary case, but with the twist that we need to disincentivize non-global budget balance prices that we allow in our setting, and this consumes a large portion of our probability mass, which is of order 1 minus 1 over epsilon squared. This leaves us with a probability mass on 1 over epsilon squared that we can use to play hard instances inspired by the one developed in the smoothed adversary case, in which we have k candidate prices, which are the orange region in the picture, and but they do not come with any interesting feedback, while the only feedback that we can collect is from the red regions, which however incur in large regret. By setting accordingly all the quantities, we get the t to the 5 over 7 regret lower bound. We also analyzed the guarantees with respect to a different benchmark, which is the best distribution over prices, which in expectation is global budget balanced. And this is inspired by the bandit with knapsack line of works. And the negative results here is that we must incur in linear regret for a small constant epsilon larger than 0, but by black box reduction from the two benchmarks, we can prove a positive result, which is that our algorithm incurs in a 2 regret with respect to this this stronger benchmark. To conclude, let me summarize the key contribution of this work, which is to show a strong relation between gain from trade and revenue, which allow us to design a two-phase algorithm in the adversarial setting, And we achieve this by showing that revenue maximization is strongly linked with social welfare maximization. And this, for the first time, gave us an algorithm that achieves low regret in a very natural setting of global budget balance.